In this chapter 2 we will study about stress and strain for axial loading cases, and contents what we will study: stress and strain for axial loading. Here we will study about the stress strain and relationship for axial loading, and what is normal strain, stress strain test, stress strain diagram, ductile materials, brittle materials. In this diagram we will understand what is the difference between the behavior of a stress strain graph for ductile material and brittle material. The next one is Hooke's law. What do you mean by Hooke's law? And from Hooke's law, how do we determine the modulus of elasticity? Those things we can understand from this slide. Elastic versus plastic behavior. We will understand the difference between elastic and plastic behavior. In elastic behavior, how the material behaves, how the stress strain diagram is there, the linear relationship is there. Those things we will understand. The next, fatigue, deformations, and after that we will study about the sample problems for different examples. And here we will understand like stress and strain for axial loading. Suitability of a structure or machine may depend on the deformations in the structure as well as the stresses induced under loading. And this means how the suitability of a structure or machine, if deformation is more, whether it will function properly or not, whether the structure will withstand the forces, intended purpose is satisfied or not. Those things we will study about here, as well as stress induced under loading. When you apply a load, there will be a introduction of stresses. That also you will study it. Statics analysis alone are not sufficient. Here, what does it mean, static analysis alone or not sufficient mean? It means like if the loading is dynamic, then static stresses alone, it will not help us to understand the complete behavior. Considering structures as deformable allows determination of member forces, reactions which are statically indeterminate. Actually, the deformable, if you apply any load on some particular structure, there will be a deformation. So we need to find out the determination of internal forces reactions, some cases which are statically indeterminate structures. Determination of stress distribution within the member also requires consideration of deformation in the member. For example, on member, how the stress is distributed within that member. To determine that one also, we need to understand how the deformation in the member is happening. And chapter 2 we will concern about the deformation of a structural member under axial loading. If you apply the axial load, how the structure deforms, that we will study about it. And later chapters will deal with the torsional and pure bending loads. In this chapter we will study about the axial loading. Then next chapters we will study about the torsional and pure bending loads. Here you can see there is one bar with fixed at B and A is free end. Once you apply the load of P, it will elongate delta from the original length L. This delta is the elongation, so new length is L plus delta. So what we understand, the stress means stress is nothing but this force divided by this cross-sectional area. That gives the load per area, that becomes the stress. Actually it's a load per unit area, that's a stress we call. Then strain is nothing but how much it deformed in relation to the original length. If for example original length is 1 meter and deformation is 1 mm, means 1 divided by 1 meter, that 0.001, that's a strain. And here you could see if I apply 2p, load is twice the times what we have seen in figure 2.1, and the area is also, if it's twice, then we could see the stress is 2pa divided by 2a. is nothing but P by A, and elongation also delta by L. So it relatively the load also increase, the stress area also increase, but the stress remains same. And in this case, if we increase the length, this is the force, this is the area, so P by A, stress becomes P by A, and length is 2 times the original length, and deflection also 2 times. So what will happen? This deflection, deformation divided by length, so delta by L, that becomes strain also same. So in all these cases, stress and strain is same, even though it's a different forces, different cross-sectional area. So here what we are going to do is this stress strain test setup. The test specimen with the tensile load. This is the specimen. Here it is connected to the 2 ends with these machine parts and threaded portion, so it tightens. So when we apply the load like this P, it will try to elongate between these 2 points. This is how we will find out the this is how we will do the tensile test, and this machine is used to test the tensile test specimen such as those. So in the next chapters, this is the specimen with the tensile load, this is the length. We will come to know how much this length is elongating at different loads. So once you start apply this increase the load, that means stress, deformation also it just starts increasing. After some point of time, there is a permanent set yield that we called. After that, once you still, it takes more load from here to here, you can see almost 60%, 40, 20, 60 means almost 20 times, 20 difference, it increases with more deformation. That's called strain hardening. After that, after some point of time, it becomes, even the load we cannot apply, it is necking, it is rupturing it here. So this is how the behavior of a low carbon steel it happens. The same thing for aluminum alloy, the behavior is like this. Here there is some clear distinction of field value, here it's not that much clear, but until some point it becomes linearly proportionated. That means if you apply load 1, deformation also unit comes same amount. If load 2, 2 times the unit. Here also until some portion it is linear, after that it's non-linear. So aluminum alloy stress strain curve is non-linear. And brittle materials. Stress strain diagram for a typical brittle material. It also increases stress and strain, but it is not linear, it's curvilinear. After some point it suddenly ruptures. There is no strain hardening, necking, all those ductile, like so much of elongation is not there. Strain portion is very less. That means it suddenly ruptures. This is the rupture material behavior. Here Hooke's law, it says that modulus of elasticity, Hooke's law, for pure iron, this is stress strain curve, carbon steel, high strength steel, and constant tempered alloy steel. Below the yield stress, strain is proportional to stress, and stress is proportional to strain, with the constant of E. That E is nothing but Young's modulus or modulus of elasticity. Stress strain diagrams for iron and different grades of steel. This we need to understand, like stress and strain is proportional, directly proportional with Young's modulus. So if you increase the Young's modulus and the strain is more, the stress also gets more. If you take this strain this way out, then stress by strain is nothing but the Young's modulus. Strength is affected by alloying, heat treating, and manufacturing process, but stiffness is not. If you could see, this is the linear portion with the different alloying and heat treatmenting. This is different heat treatment. Pure iron, this is different alloying and heat treatmenting and manufacturing process. Strength varies, but not the stiffness. Modulus of elasticity is not. Elastic versus plastic behavior. If the strain disappears when the stress is removed, the material is said to behave elastically. That means what? If you remove the load, it goes back to its original position, then it called elastically behavior. If the strain disappears when the stress is removed, once you remove the stress, strain disappears, then the material is behaving elastically. This is how we can define the elastic behavior of a material. The largest stress for which this occurs is called elastic limit. Here there is some stress limit. Until that it can go back, the strain will be removed if you remove the stress. Thus the largest stress value is called elastic limit. When the strain does not return to zero after the stress is removed, the material is said to behave plastically. That means when the strain does not return to original zero, that means it does not return to the original length, it is said to be behaving plastically. Once you remove the stress, the material has to go back to zero strain. That's called elastic. If it doesn't go back to zero strain, the behavior is called plastic. The fatigue curves, you can see that fatigue properties are ASN diagram: stress and number of cycles. Stress in vertical axis and number of cycles of completely reversed cycles in horizontal axis. This is how the stress strain behavior of aluminium and steel. Steel, it has something like bilinear. Aluminium is almost like a single linear. A member may fail due to fatigue at stress levels significantly below the ultimate strength if subjected to many loading cycles. If you take this steel member with the number of repeated cycles, the strength degrades. At lower, member may fail due to fatigue because of repetition of cycle. It experiences fatigue. So at less stress levels itself, at stress levels less significantly below the ultimate strength, that would fail. If it is subjected to multiple loading cycles, that would cause fatigue. When the stress is reduced below the endurance limit, the fatigue failures do not occur for any number of cycles. That means if you apply less number of cycles, it's below the endurance limit, so it does not have any impact on the stress values. When the stress is reduced below the endurance limit, the fatigue failures do not occur for any number of cycles. Even if you apply the load for a million numbers of cycles, but the stress value is very less, then it will not cause any fatigue, because this is called the endurance limit. Deformations under axial loading. You could see from Hooke's law, stress is proportional to strain. So strain is nothing but stress by X modulus. So stress value, we can say P divided by A. So stress equal to P by AE. Then from the definition of strain, what is strain? It's change in length divided by original length. So change in length delta divided by original length. We can see equating and solving the deformation. We can get the deformation value. If we equate the strain value P by AE and delta by L, we can get PL by AE. That's the value for deformation. So stress is proportional to strain. So strain is nothing but stress by Young's modulus. So stress, we are getting P by A. So strain is nothing but PAE. So we can get it from the Young's modulus and the force and area. From that itself we can get strain P by A into 1 by E. So stress into P by A, load by area, into 1 by Young's modulus value, we can get the strain. This is how we can get the strain, P by AE. And here also we can get the deformation divided by length. Even if you don't get the deformation, also we can see from here itself the strain value. So once we get the strain value, strain into original length, we can get deformation. So once you calculate the strain and multiply with the original length, we can get the deformation value. With variations in loading and cross-section or material properties. So if there is a change in the material property, or change in the force, or change in the cross-section areas, or change in the length, we can see the stress variations in cross-sections. Here we could see determine the deformation of a steel rod shown under the given loads. This deformation we will calculate. This is one cross-section area, this another cross-section area with different length. So divide the rod into components to the load application points. Apply free body analysis of each component. Determine the internal force. Evaluate the total component deflections. So divide the rod into three components. 1, 2, 3. So this is 130. If I take the cross-section area here, I will get 130. If I take a cross-sectional here, what will happen? 130 like this, and 200 is like this. So we will get P2. If I take cross-section here, 130, 200, 300, and 330. L1, L2.3, A1, A2, L3, A3. So we are getting P1 is 130 minus 200 plus 330. So 460 minus 200 becomes 260. That's okay. P2 130 this way, 200 this way, so minus 70, and here 130 value. So total deflection is PL by AE. So P1 L1 and by A1, PL P2 L2 A2, P3 L3 A3. So we can get 1.775. Sample problem 2. The rigid bar BDE is supported by two links. This is one link AB, and the CD is another link. So this is the rigid bar BDE supported by two links AB and CD. Okay, link AB is made of aluminium. AB is made of aluminium. Okay, and has a cross-section area 500 mm². Link CD is made up of steel. Say the aluminium is 70 gigapascal, steel is 200 gigapascal. So steel has more Young's modulus than aluminium. The force 30 kilonewton is shown here. Determine the deflection at B, D, and E. Apply the free body analysis to the bar BDE to find the forces exerted by the links AB and DC. Evaluate the deformation of links AB and DC, or the displacements of B and D. Work out the geometry to find the deflections at E given the deflections of B and D. So free body diagram BDE bar is that AB FCD 30. So summation about moment B. If I take the moment would be FCD into 0.2, 30 into 0.6. This is the clockwise moment, this anti-clockwise moment. So we will get FCD, this force. This force you will get it 960 kilonewton tension. Then if we take moment about D, FAB into 0.2 and 30 into 0.4. So FAB is in compression. If you apply here, it will go up. About this point, it will go up. This will be in compression. This will be in tension. So it will go like this. So it will push, it will try to pull. So this is in tension, this is in compression. displacement of B at point B. What would be the displacement? So delta B equal to PL by AE, P 60 and L, A, E, all these things, it comes 0.514 mm. This minus sign, that means goes upward. This goes upward, 0.514. Next, displacement D. D is what is the force inside? That's 90 kilonewton. That's compression, this is tension, so it comes 0.3 mm downwards. So it goes upward 0.5, this goes downward 0.3. So it becomes like this, 0.3, 0.5. So here you can see this is 0.3 and this 0.14, then this delta E, we will find it out. B dash equal to D dash, B dash divided by D dash equal to B H and H D. So we are taking this portion, this ratio, and then this ratio. This is 200 minus this, we do not know from where it comes. X root 73.7. E dash D dash HE HD. From there you will get delta E equal to 1.92 mm downwards. Static indeterminacy. The structures for which the internal forces reactions cannot be determined from the statics alone are said to be statically indeterminate. In this structure, if you see here, we cannot find out the internal forces and reaction by static alone. So this one, if you see it here, there is one reaction or B. Here also it's holder, so 300. This we can put like this, 300, 600. It will, because of this forces, it will move up, and there is some reaction is coming. This delta is 0, right? At this point this is 0. So to make this 0, some force is acting. If this is not there, it will be elongated. So this delta L downwards and this delta R, these two are equal. I mean delta L plus delta R equal to 0. The structure will be statically indeterminate whenever it is held by more supports than required to maintain its equilibrium. You understand? If the structure is supported by more than required number of supports, it becomes indeterminate. Redundant reactions are replaced with unknown loads, which along with other loads must produce compatible deformations. So this is the unknown reaction that we will put into the reaction as a unknown force. We will replace the redundant force. This is even if it is not there, it will be hanging. So this one we will replace it with loads that produces compatible displacement. If R produces delta R, this reaction RB produces delta R, this loading produces delta L, these to be equal. Deformations due to actual loads. These are actual loads. Because of these actual loads, what is the deformation? And because of the redundant force, what redundant reactions, what is the deformation? These two are determined separately, and then if you add it or superpose, that becomes 0. So this we will analyze this as a two separate structures. Determine the reactions at A and B for the steel bar loading, assuming close fit at both supports before the loads are applied. 300 delta R plus. Consider the reaction at B as redundant. Release the bar that support. Solve the displacement at B due to applied loads. Because of these applied loads, we will find out the displacement here, 300, 600. So we know this PL by AE, this PL by AE, so we can find out this displacement. And reaction, if you apply this PL, this L by AE, whatever the displacement, and here there is no force, but the same force is coming, we can find out the reaction. Recur the displacement due to loads and due to redundant force must be compatible. That recur, that is that sum must be 0. Solve for the reaction at A due to the applied loads and the reaction at B found. So P1 equals 0, P2 and P3 equals 600 kilonewton. 1, 2, 3 in third location. P4 is 900. So A1, A2, same, A3, A4, it's the same. L1, L2, L3, L4 equal to 0.150. It's equally distributed. So we will find out, solve for the displacement at B due to the redundant force. P1 equal to P2 equal to minus RB. So this is the redundant force. So if we equate these two, our reaction becomes 577. At here it becomes 577 out of 900. 600 becomes here almost 580, right? It's less than 600. So top also it goes, RA will become 323. RA or B will find it